Okay, good morning, everyone. Well, it's my honor to be chairing the very last session. And at this point, I guess almost everybody knows each other, so no introduction is necessary. But our first speaker is Shantanu Mukherjee, and he will be telling us about unconventional superconductivity in dichalcogenides.
Thank you, Turan. As Turan already introduced, I'm Shantanu Mukherjee, and apologies for not having more information on the title slide because it was a bit of a rushed work. So I work at IIT Madras, and I wanted to kind of go a little off the scale from the basic theme of the conference and essentially talk about the story, a little bit of story of dichalcogenide superconductors. It is not entirely off the scale because, as you will see, we'll be talking about charge density wave. We will be talking about unconventional superconductivity. And although we'll not be talking about flat bands as such, we'll essentially be discussing a bit about strong correlations in this system. So when I'm discussing the story of dichalcogenide superconductors in the context here, I'm essentially interested in the problem of superconductivity in these dichalcogenide materials for the 2D versions of these systems. So, for example, monolayer niobium diselenide and tungsten disulfide and various others, in which in the last few years, a lot of interesting physics has been discovered, and there have been kind of discussions or observations which are hard to reconcile within a conventional pairing mechanism for superconductivity. So for the part of the work I'm going to be talking about, a significant amount of calculation for the normal state or the CDW state was done by Buddhadev Devnath, who's a graduate student in my group. And for the superconducting state was done by Shubhajit Roy, who's again a graduate student in my group. And the work for the superconducting part had invaluable contributions from Brian Moller Anderson and Andreas Kreisel. So these two gentlemen are in IIT Madras right now. These two, I'm not sure where they are. So maybe somewhere around. Okay. So, and also I'll like to mention that for the CDW state, I had invaluable contribution from Professor Ranjit Nanda's group and his graduate student Mayank Agarwal. Okay, to start off the story of monolayer NBSE2, if you have not been following the literature so closely in the last few years, what made this material interesting compared to the bulk version? So the bulk version is a well-known conventional S-wave superconductor driven by electron-phonon mediated pairing mechanism. For the monolayer system, however, when you go to essentially this limit, what happens is that the niobium lattice that you have out here, the seleniums are sitting in a position so that for every position R, there is not an equivalent selenium at minus R position. Now, what that leads to is effectively the lattice structure for this 2D material that you have. So this is like a side view of this particular structure. The lattice structure of this 2D material breaks the inversion symmetry for this particular system. So this is a non-centrosymmetric crystal structure. But additionally, although it is a non-centrosymmetric crystal structure, if you look at the side view of it, the niobium and the selenium layer, you can see that there is a planar reflection symmetry about a plane like this. What that leads to is that if you want to consider the story of spin-orbit coupling in this system, and the generic form of the spin-orbit coupling means that you cannot have an electric field which generates the spin-orbit coupling, which is out of the plane. It is primarily in the plane. And the effective magnetic field that this term creates would be out of the plane. So result of that is, so because the momentum of the electrons is also in the plane, so the P cross E is going to be out of the plane. And that is going to couple to the spin. And what that's going to lead to is that it's going to polarize the spins at the sides out of the plane of this monolayer NBSE2 system. Now, this spin-orbit coupling causes a spin momentum lock structure, and it causes a band splitting in this particular material. And because of this up-down arrangement of the spin, which is different from your Rajba type of interaction, this has been termed as a Ising spin-orbit coupling. Now, what this does is, of course, this is a non-magnetic material, so the Kramer's degeneracy has to remain intact. So for every point k with spin up, there is an equivalent point, minus k with spin down, but because of the spin orbit splitting, these two correspond to two different bands in your system. So if you look at the electronic structure generated from DFT, there is primarily, at least at the level of ignoring or not having a spin orbit coupling, a single band which forms the Fermi surface of the system, which creates a pocket centered at the gamma point and pockets at k and k prime points. And additionally, if you now include the effect of spin orbit coupling, you see that the pockets created by the single band split up into these red and blue pockets out here. You can think of the red pocket corresponding to a spin up state and the blue pocket corresponding to the spin down state because of the spin momentum locking. The way the Kramers degeneracy works is that for a point k, let's say out here, with a spin up at minus k at the point out here, it is a spin down, right? So that is your Ising spin orbit coupling playing out in the momentum space. Now, this is overall the basic idea of what's going on in the structure and electronic structure of this material. Experimentally, also, there have been some very interesting things discovered in the last few years. One of them is that if you go, let's say, start off with a bulk material, and you were to kind of measure the transition temperature for the charge density wave instability and the superconducting instability and reduce the number of layers. One thing that always shows up is that the charge density wave transition temperature goes up, whereas the superconducting transition temperature mostly stays almost unchanged. It shows a relatively small dip as you go over to the monolayer limit. This in itself is interesting, right? You don't have any significant suppression of the superconducting instability, and this particular point, which this is in a log scale, it's not so clear, but this is a strong enhancement. This point would be around 33 Kelvin, and here we are talking about, I don't know, 135 or 140 Kelvin enhancement of the CDW transition temperature. For the superconducting transition temperature, the bulk material TC is around 7 Kelvin, and once you go to the monolayer limit, the early work showed that the TC might be about 1 Kelvin, but now they have got cleaner samples. They say the TC is around 3 Kelvin, so it's not a significant change in the TC. Now, this is the typical phase diagram as a layer number that is shown by this material. If you now look at the CDW phase, the nature of the charge density wave in this system is a structure which shows a 3Q charge density wave order. That means essentially there are three ordering wave vectors, 1, 2, and 3, which are related to each other by 60-degree rotations. And if you Fourier transform...
What is known about the transition various states?
Sorry, which states?
From superconductor to CDW to metal?
Are they, you mean?
The second order?
It's a second order transition.
All of them are second order?
Yeah. That's known. Yeah.
And the metal is an ordinary metal?
It's an ordinary metal.
It's a Fermi liquid?
Yeah. So there is no non-Fermi liquid physics playing out. So this is your CDW state, and if you Fourier transform it, you can see the Bragg peaks that are generated by the CDW state ordering out here in addition to the structural Bragg peaks. And effectively what it means is that the CDW state itself is not breaking the lattice symmetry that you're dealing with for this problem, right? But then there are certain interesting features that come out. For example, something which is not seen in bulk NBSE2, although you have a 3Q CDW phase, is that if you look at the edges of this material, and if you were to do a scanning tunneling microscopy experiment from the edge towards the bulk, near the edge it forms these stripe-like patterns. Now, in this particular paper, they argued that these strike-like patterns are not simple result of some kind of a Friedel oscillation happening from these edges, and this they argued based on the fact that effectively the stripe-like patterns also maintain a 3-unit cell periodicity. So they tried to show from some simple calculations that from a Friedel oscillation, since the physics would be governed by the inverse Fermi wavelength, this type of pattern would be expected. However, they also found that if you look at the energy dependence of the STM features out here, the energy dependence essentially shows that it's not energy independent. Right? If you go to, let's say, a very different energy scale, you recover back the 3Q order. It's only in an energy window that the stripe-like pattern is observed. So it is kind of, it depends on how you look at it, whether you look at it as a 1Q stripe order or essentially some energy dependent modulations. Now, this is the sample on which they looked at the STM out here. And then if you look at the density of states in the CDW phase, you find that in fact near the zero energy, there is some form of a gap opening leading to a dip formation out here, but various studies have shown, including first principle calculations, that the gap formation is not complete, which typically represents that the gap formation is anisotropic on the Fermi surfaces. DFT calculations for the bulk material have also indicated that the gap primarily opens near the K and K prime point of the Fermi surfaces I showed you a few slides back. Okay, so that's one. Now, for the superconducting state, this was one of the papers in 2022 which generated quite a bit of interest. And this was, again, STM measurement, where they looked at the local density of states in the superconducting state, and they essentially found evidence of the presence of collective modes or Leggett modes in the superconducting state. And they did an analysis based on the higher harmonics of the Leggett mode and found out that there is an anti-correlation with the evolution of the superconducting gap and the energy corresponding to the Leggett mode. For example, if you put a magnetic field in a system which suppresses the gap, they found that the Leggett mode energies simultaneously move outwards, which they argued that for you to have a Leggett mode in your system out here, you cannot explain it by the presence of a conventional S-wave pairing mechanism. You need some unconventional pairing or some kind of a strong anisotropy to be there in your superconducting state. So they claim that they can explain this idea by considering that, remember that this is a broken inversion superconductor. So this can naturally mix your even and odd parity superconducting states. So they said that there is a mixing of a F-wave triplet to the S-wave singlet state out here, and which can lead to essentially using an equation of motion method of frequency and formation of Leggett mode along these lines. So this paper, in that sense, was a first proposal that there is some unconventional pairing mechanism that is happening in the system which we need to understand better in the monolayer system. First principle calculations had already shown before by Igor Mazin's group and others that if you look at the susceptibilities in the system from first principle, there are strong fluctuations, spin fluctuations there in the system, which are not present for the bulk material. So the question was that, how do we understand any unconventional contribution to the pairing? So this was a theoretical work by Igor Mazin's group and Dan Achterberg, where they essentially showed that if you now start off with a pairing mechanism where you consider the pairing is due to electron-phonon interactions in your system, then for this pairing mechanism, you can show that single gamma, the gap on the gamma-centered pocket is much smaller than the superconducting gap that you have on those K-centered pockets. So what they did was they considered electron-phonon interaction, which they extracted from first principles calculation, pairing mechanism in the repulsive spin fluctuation mechanism, which they took from an average toner. So it was momentum independent, a constant repulsive interaction. And from there, they essentially showed that you get a gap like this. And then they argued that you don't necessarily need a singlet triplet mixing to understand the formation of these Leggett modes, but the strong anisotropy between the gamma-centered pocket and the K-centered pocket can also lead to an effective free energy approach that can give you modes or in-gap states which are less than delta. Okay, but the question was that they necessarily needed a gap on the gamma-centered pocket, which was much smaller. Then this was another experiment that was, which has actually been seen in other dichalcogenide Ising superconductors as well. And this experiment is that, let's say you take a magnetic field in the plane of the material and you rotate it and you measure thermal magnetoresistance in the system. What you find is that as a function of magnetic field, there is essentially this clear twofold structure that shows up, which indicates towards formation of a twofold symmetry in the superconducting gap. In zero magnetic field, the gap shows a hexagonal symmetry as we would expect from the lattice. But in a magnetic field which is in the plane, you have this twofold. Now, if you look at essentially the irreducible representations of your system or all possible superconducting gaps, it is very hard to reconcile for a conventional mechanism the formation of a twofold gap out here. First of all, you need a multidimensional representation, but within that multidimensional representation, you need a scenario where it chooses essentially one of the 1I states. It does not choose one of the 1I states to get this possibility out here. In this particular paper, they said that probably it is a multidimensional representation playing a role, but even for that, it won't work for a weak coupling ground state. So the question remains that what would be the solution? Lastly, if you look at the superconducting TC as a function of, for example, a non-magnetic impurity like silicon sitting on the sample, as a function of silicon concentration, the superconducting gaps in local measurement seems to go up and then to go down. Now, this in itself is interesting. You can say that this probably comes in from the fact that maybe the CDW is getting suppressed, so there is lesser competition between CDW and superconductivity. But then again, if the CDW is getting suppressed and you have a conventional S-wave order, you do not expect this type of behavior to show as a function of non-magnetic impurity concentration. So this is also an evidence that there is more to the story. Yeah.
Is that an average of the gap? Do they have any homogeneity because the sample is quite disordered?
Yeah. So they are essentially looking at the average of the gap over the sample, considering it to be proportional to what is suppressing the TC in the system, and then looking at it.
Okay.
So yeah.
Thank you.
So it's a non-magnetic impurity. So the expectation is that in an effective Abrikosov-Gorkov theory, that is what is contributing.
Thank you.
So these are the questions. I won't kind of read them. You got the basic idea that there is a question first because of the large enhancement of the CDW transition temperature. What is the mechanism for the formation of CDW? What role does electron-phonon interactions play in the system? What is the nature of local effect near non-magnetic impurities? Does it retain the lattice symmetry, for example? And can the CDW lead to stripe-type charge ordering near sample edges that you saw in the experimental measurements? Now, the model that we chose for this particular system is a tight binding model, and the low energy model, which kind of reasonably or pretty accurately actually reproduces the density functional theory derived band structure at low energies, at least for these gaps. This material is lucky to have a relatively large splitting between these high energy conduction bands and the bands which cross the Fermi level. You need to consider minimally 3 orbitals sitting on an IOBM, the x square minus y square, xy, and z square. And additionally, you have to include Ising type spin orbit coupling in the system, which primarily couples the x square minus y square and xy orbitals. From first principle calculations, the form would be more complex than this, but I mean, so the form we use is more complex than this, but you can actually see the structure. Now, if you look at the charge susceptibility for the system, one of the things that come out is if you just look at it from a nesting-driven picture, you do not get a maximum peak in the CDW at the CDW wave vector in the charge susceptibility. It is, so 2/3 gamma m would be around the point where the CDW wave vector lies. It is actually shifted from it. And however, very similar to the story of bulk and BAC2, if you include the effect of electron-phonon interactions in your system, then the peak bang on shifts to this 2/3 gamma m. In fact, this is still calculated as a density-density correlation from the tight binding model. If you do a more critical DFT calculations, it actually even shows that the CDW or the peak enhancement is much stronger than what you find in the bulk system. So it seems that the CDW physics, at least, is being driven by electron-phonon interactions in the system, and you can see the effect of it if you calculate the electron-phonon coupling amplitude over the Brillouin zone. They are very strongly peaked at the 2/3 gamma m. That's where the renormalization of the susceptibility from the electron-phonon interaction leads to the CDW also forming at that wave vector. Now, to model the CDW state in the real, I'll just quickly go over this. We convert it to a lattice model, including a CDW instability. We calculate self-consistently by having a pairing term, and this m factor that you see out here goes over the 3 wave vectors in the 3q CDW state. So then for this lattice model, when we look at it, you can stabilize on a lattice this 3q CDW state nicely, And if you look at the density of state, which is averaging the density of states over the entire lattice, you get a peak happening around the same point you see in the experiment, a dip feature, which is not a complete dip, representing a very anisotropic CDW formation. Interestingly, if you now ask what happens in the presence of non-magnetic impurities, since you have a 3Q CDW state, and if you look at your lattice, there are actually 3 inequivalent impurity sites that get generated. And if you were to try to calculate, let's say, self-consistently what happens to the CDW order parameter or the electron densities near these, you find that locally, 2 of these sites out here lead to a local structure which has a 6-fold symmetry in it, but from this particular point itself, if you have a non-magnetic impurity, you get these clear-cut 2-fold symmetry forming in the local Fourier transform. Now, the interesting bit is, if you were to now ask the question that is there then inherent 2-foldedness in the presence of non-magnetic impurity? Probably not true for global measurements, because there would be 3 equivalent 60-degree rotated structure of this type of 2-foldedness. So if you are doing a global measurement of magnetoresistance, they will average out. What is interesting is, if you were to put an in-plane magnetic field in your system, there is a spin-orbit coupling. Can those 3 equivalent 2-folded regions become inequivalent or not, right? That is also a quantitative question, not just qualitatively. So then you can also look at the stripe order near the sample edges, and what you find is effectively the local density of state shows in the CDW order parameter is not clear, but if you calculate the local density of state as a function of site, you can see that you clearly get these 1Q type of stripes forming, and in fact they very nicely show an effective 3-unit cell periodicity to form. And we also see that these stripe formations are quite energy dependent. You can get to energy regime where you retrieve back your 3Q type CDW order. So overall, it seems that at least partly within such a mean field real space lattice model, which includes the effect of the Ising spin orbit coupling and models the CDW self-consistently, some of these features you can have some qualitative idea where they are coming from. But the question of superconductivity is a little more complex. I'll very quickly go over to the basic formalism that we have. Again, you start off with a Hamiltonian, which is the tight binding Hamiltonian corresponding to the 3 orbitals. And your superconducting pairing kernel is this quartic term out here, which has been kept completely generic. No particular symmetry channel has been assumed for it. And this, then if you do a mean field decomposition of it, leads to a gap function, which would be of this form, which all of us know. This is just a generalization of the BCS theory that you do. So this particular piece, we calculate along the lines of looking at a spin fluctuation mediated pairing mechanism, primarily summing up all the bubble and ladder diagrams to include spin and charge fluctuations within our model. So you get a momentum dependent pairing interaction in the repulsive channel coming out from here. Now, I won't go into the details of it, but you know that as Brian also talked about a couple of days back, that this pairing interaction is proportional to the susceptibility, charge and spin susceptibilities in your system. And effectively, the charge and spin susceptibility peaks at a point which is very close to this 2/3 gamma m in our system. And these would, of course, also be dependent on the on-site Hubbard U and the Hund's coupling J in your system when you calculate this. So you, let's say, plug this into your Hamiltonian, and you, let's say, use Gorkov equations to derive your BCS gap. Then the most generic BCS gap that you get, if you assume that the single particle Hamiltonian has a spin orbit coupling but does not have spin flip terms in it that you can have in Rajba, is a gap which looks like this. It doesn't look exactly like the BCS gap we have seen out here. You can derive the BCS gap by just choosing inversion symmetry, which means that this energy is equal to this energy. You'll get your standard BCS gap, but it is slight generalization that comes in. Now, you also notice very quickly that the superconducting pairing that you have out here is of a form of Ck spin up, C minus K spin down. I'm, for simplicity, not putting in the band indices out here. But this does not allow you to write down the gap function in effectively a singlet or a triplet form. The reason is that if you consider a singlet with a minus sign out here, for C, you need a Ck down But since for a given band, if you have a k up, for the same k, you do not have a k down, right? They are spin momentum lock states. So effectively, the system doesn't allow you to write or decompose the channels in terms of singlet or triplet. You have to look at this expectation value and extract effective singlet or triplet physics from it. The gap equation is kind of, as you can expect from this full formalism, a little more complicated with off-diagonal and diagonal contributions that come into the picture. And if you were to consider, let's say, the scenario for first ignore spin-orbit coupling in your system, then the gap function, I show you what are the solutions that come out by diagonalizing this gap function, which is equivalent to diagonalizing this matrix that you see out here, as these solutions. So there would be a lot of solutions come in where the ground state energy is given by the largest eigenvalue in the problem. So that is this 5 minutes. Sure.
If you follow this.
Yeah, no, it's okay. So the ground state solution is given by this, and you can see that for the ground state solution, indeed you find that for the gamma-centered pocket, the gap magnitude is much smaller than what you have for the k-centered pockets. This was along the line that for a slightly different mechanism, Igor Mazin and Dan Actaber's paper, they were arguing for the presence of the collective modes. But the ground state here belongs not to the A1G or the S-wave representation, but to the A2G irreducible representation of the D6H point group. I write D6H because for this solution that I'm showing, I'm ignoring the spin-orbit coupling for the moment. So the lattice symmetry is not reduced. Now, again, you can see that for this is indeed even parity solution. So this can be decomposed into even odd parity because spin-orbit coupling is ignored. And for the even parity solution, the odd parity solution are far lower in energy. So it is along the lines of an even parity A2G solution with a small gap on the gamma-centered pocket. Now, if you were to consider, let's say, the same Coulomb interaction parameters and switch on the spin-orbit coupling and actually solve this big matrix, without spin-orbit coupling, these were negligible, then effectively you find the solution actually changes significantly, which is quite surprising. The dominant solution primarily belongs to what is called as the two-dimensional E prime representation. I don't call it E2G or E2U because effectively this is the D3H point group that we are dealing with spin-orbit coupling. And the ground state energy, because of the two-dimensional representation, is twofold degenerate, right? There are two solutions that come out for the lowest energy solution. So it seems that the dominant solution is like this, and it naturally, a E prime representation for a D3H automatically mixes the E2G and the E1U solutions of the superconducting state. How much is the mixing is a different question. Now you can, but then those are not the only solutions. I showed you the solutions at U equal to 1. If you look at the solutions as a function of U, you find that the solutions do change. Effectively, the symmetry of the solutions does not change significantly, is what we find. But the solutions that I show on this region, so this is without spin-orbit coupling, this is with spin-orbit coupling, and the solutions that you have for low U versus the solutions that you have for the high U are primarily the same irreducible representation, but with larger mixing of the odd parity contributions, triplet contribution. It means that as you increase U, the triplet mixing in your superconducting gap grows. We also find that as a function of Coulomb interaction, the larger Hund's coupling increases the amount of mixing of the triplet channel in your solutions. Okay, so you can calculate the density of states, and you can show that if you were to take the weak coupling ground state, as it is called, if you were to consider a fourth order free energy, that has the A1G symmetry as it is expected for the two-dimensional representation. Again, what you can also do is you can locally approximately consider the gaps to be singlet or triplet by considering the value of the gap at very close by k points, and you can from that evaluate an effective triplet and singlet component. And when you do that, so what you essentially do is you calculate the gap out here as delta up down, gap out here as delta down up, and then you take difference and sum of those to generate an effective piece which is triplet singlet. And you find that this eta parameter, which would be proportional to the ratio of singlet triplet, that means if it is a pure singlet it is 1, and if it is a pure triplet it is -1, it goes from a dominantly singlet to a dominantly triplet solution. So then we looked at the magnetic field dependence. I won't go into the details of it, but the point I just want to make, I don't want you to look at all of this. point I want to make is that even if you look at the in-plane magnetic field component and you want to do, or even restrict yourself to a homogeneous solution, not look at the FFLO or other phases, you cannot separate out, in principle, the magnetic field dependence from the gap matrix itself. They will be there. You have to, if you want to work with the Eilenberger type of formalism, you have to approximately separate out singlet triplet. But what we have tried to do out here is we have tried to solve the full gap matrix with the magnetic field without using that approximation. So then what comes out is, and at the limit of it, where you assume a singlet solution, you get this expression, which you will find has been used extensively in the literature to look at the effect of Zeeman field in the system. So this assumes that this Ising coupling is independent of K, and effectively the state is a spin singlet. So, and you get this physics coming out for the, I mean, we don't have enough time, so I'll just tell you that if you ignore spin-orbit coupling for the singlet state, you get essentially this well-known behavior, which was first shown by Mukherjee, probably in the 1960s. And for the triplet states, it becomes independent of field. But if you now include the effect of spin-orbit coupling, at low temperatures, you get extremely large upturn. For real systems, you can show that in the presence of disorder or in the presence of essentially, which reduces the strength of spin-orbit coupling, that upturn can be significantly reduced. But this upturn is there and has been seen in many dichalcogenide superconductors. So with that, I think I'll just display the summary slide.
Very nice talk. Can I ask something?
Yeah, sure.
So so this gap equation you wrote down, if I just do a simple Born approximation there for the disorder, can you reproduce this non-monotonous?
Yeah, we haven't tried. We have only looked at the single impurity physics out here. But if you want to essentially do Abrikosov-Gorkov type of theory for this,
by just putting
with Ising spin-orbit coupling,
yes,
and so on.
Yeah.
I don't know if it has been done, but yeah, that's something which could be interesting to look at. But then, yeah, it's another question is that if you now want to also keep CDW is an important parameter in the problem,
right,
for the TC dependence, it will get exponentially complex numerically.
Right.
Any other questions?
Can I ask one more? Sorry.
Yes. Yeah, sure.
We have.
Yeah. So, see, are there any metallic phases around where you're actually doing this calculation? Why I'm wondering is the following. You have this very interesting feature that you talked about. I was wondering whether in 2D, some electron multifractality, whether that can...
It has actually the paper that I showed you, the TC dependence from. In that paper, it's in the Nature Physics paper, they argue that this physics is coming from multifractality.
For the multifractality of the metal incident?
Of the metal, yeah.
So I have a couple of quick questions,
sure,
actually. So the first one is about the Ising spin-orbit coupling, which is pretty much well established in these systems, as I understand. But in some non-central symmetric systems, there's no linear spin-orbit coupling, right? Not even Rashba, but there's just a cubic one Dresselhaus and so on.
Okay.
Is there a simple argument here that says that you must have a linear spin-orbit coupling? Because you discussed that for a linear spin-orbit coupling, you have to have Ising, not Rashba, essentially.
Yeah, sorry, I mean, probably I need to ask you, so when you say linear spin-orbit coupling, what
so
are you
it's
implying?
K dot sigma, not K cube something sigma.
Yeah, so effectively, I think from the, if you derive the spin-orbit coupling, so the only thing kind of that restricts the form of spin-orbit coupling is the symmetries, right? The planar symmetry and so on. So if you derive, I think, the overall SOC scale from DFT calculation, I just showed you the lowest order term, you can get higher order coupling terms.
But this one definitely
that preserves the
comes
symmetry.
out.
Yeah, this particular reduced term does not. But for the superconducting problem, we have not worked with this term, but the term quantity that comes out from DFT, which Andreas essentially can tell you more about from the DFT perspective.
Okay, thank you. And if there are no other questions, I have another one about the charge density. Oh, is there? Great.
Hi, thank you for the nice talk. I still don't understand the argument that these oscillations are not QPI. I mean, they are energy dependent and...
Sorry, which oscillation?
I don't understand why the argument about why the oscillations in your the oscillations near the edge states are not QPI. I mean, they're energy dependent and they are oscillations that are occurring parallel to the edge state. And
You mean for the collective mode experiment?
yeah. I mean, it's your first summary. You say that the local density of states is oscillating, and these modulations are some other effect other than QPI and
Non-trivial.
other than quasi-particle interference.
No, so,
I didn't understand the arguments there.
Yeah. So the main point that we are trying to make out here is primarily to talk about the local modulations in the real space. And in terms of the modulations that you see near the edges out here. And these oscillations that you have in principle have origin either from Friedel oscillations in your system or essentially interference between the three Q vectors that correspond to the charge density in real space, right? So you can show that if it were due to Friedel oscillations, then there are two length scales in the problem. One is the inverse Fermi wave vector, and the second is essentially the spin orbit scale. Both control the length scale of the wavelength of these oscillations. But then out here, these modulations turn out to be exactly 3-unit cell periodic. So that can only be reconciled by interference between these three ordering wave vectors after reflection from, let's say, a 1-0 edge.
Thank you.
So in some lattices, there's a very clear distinction between a bond-to-charge density wave order where you have charge on the bonds and there's a site order. So on the triangular lattice, you can still have either one, right? Yes. Is this just site order? You said it.
So yeah, I mean, the way we have modeled it in the real space lattice model, the way we take the form factor is the minimal model which reproduces the 3Q. But the form factor can have higher order bond order terms as well.
I see.
Yeah.
Okay. So, thank you.
Yeah.
Okay, if there are no other questions, let us thank our speaker once again.